Good afternoon, ladies and gentlemen, and this is my first math lesson in English, so I really hope I will be able uh, to express the content because I'm a bit emotional. I've never done it before. So let's try that. This is part of my mathematical channel, and today we talk about orders of magnitude. I think orders of magnitude are a very important topic, at least in engineering, astronomy, and I think every human being would be a better human being if you knew orders of magnitude. Trivially, now with COVID and vaccination, people confuse the probability of dying for vaccine with the probability of dying for COVID. And since there are significant orders of magnitude of difference between the two, my first thought is like, are you guys complete nuts? So let's try to see a little bit of the math theory behind that and to pragmatically see some numbers together. Okay, so what are order of magnitude? Order of magnitude is the idea of throwing away the detail of a big or a small number and just seeing roughly in which ballpark it stays. Okay, and I will have a lot of pragmatic numbers to see. This is not abstract, it's very pragmatic. So let's take the meter, okay, as the unity of measurement. So sorry if you do miles and feet, you probably need to move away. Or maybe you can think that a yard and a meter is basically the same order of magnitude. So actually, whenever I say meter, you think yard and you're still in the game. Okay? So the idea is whenever you have a number, like whenever you talk to people, how many eggs did you buy today in the supermarket? Oh, I bought 12 eggs. And how many did you buy? Oh, I only bought 2. And what is your age? My age is 43. And yours? Oh, my age is 27 or is 65. All of these numbers that we use in the common word are usually bound between, I don't know, 1 and 100-ish. So you don't get very far with those. But the real world, the universe, is much bigger than that. And there are pieces that are much smaller than that. And orders of magnitude is the only way to put everything on the same, not scale, but on the same sentence. Okay? So the idea is, don't think of the number, how tall is the Tower Eiffel? Is 312 meters. Do I care that it's 300 rather than 200, 400? No, I don't. What I care about is around hundreds of meters. It's hundreds of meters or hundreds of yards. But it's definitely less than a kilometer, right? So what you do is you take this and you say this is 3.12 times 10 at the second in meters. So meter is your measurement. 2, the thing that you really care when you deal with big and small number is this number 2. And actually this 3.12, I don't care. I don't care. It could be twice as big, twice as small. Still, it's on the order of magnitude of hundreds of meters. How tall is Riccardo? I am 1.86 meters. So Riccardo is 1.86 times 10 at 0 meter. So that means that the order of magnitude of my height is 0. And if you're taller than me, I'm pretty sure, like the tallest man in the world is 2.72 meters. And it's still around the same order, it's still order of magnitude 0. So you need to elevate 10 at the 0 power to get this number. Now, the shortest person in the world is an Indian lady from, she was born in 1992, I just read it. She is 60 centimeters. 60 centimeters is still closer to 1 meter than to 10 centimeters. So what you need to ask yourself is, am I closer to 1 meter, to 10 meters, or to 100 meters, or to a decimeter? And if you think about it, every human being on the planet is here. I mean, my newborn was still more than 10 centimeters. Maybe when you're just born, you're slightly closer to 0.1, so to 10 centimeters and to a meter. But then for most of your life, you're here. So this is the height of a human being. You see, 8 billion humans, they're all 1 meter tall. This is the fantastic word. It's the word of huge approximation. You're like, but if you approximate, you lose information. Yeah. So what is the gain? The gain is that then multiplying, like, let's say that you're applying to a job in Accenture or Google or Amazon. I think when I applied for Accenture 20 years ago, they asked me, how many tennis balls are in this room? Like, oh, wow, that's interesting. That's actually quite easy. roughly, and you give them a rough number, it's roughly, we can calculate it later. Let's calculate it together later. But that's nothing you can do without having a perfect meter if you want to answer exactly. Is 27,128. No, that's not what you want to know. It's want to know, is more like a million or more like 1,000? This will get you through that. And we will get it at the end of the day, okay? But now, back to basics. How big is the universe? How small is an atom? Now, if you use order of magnitudes, you can actually put together on the same scale how many tenths or tenths you need to get the thing. So, Riccardo in meter is 1. So, Riccardo is the center of our universe. And I chose, oops, my son's car, sorry. So, I chose Riccardo because I am close enough to 1 meter. I could have chosen this closet as well, which is also 1 meter, 2 meters tall, which is 2 meters and 1 meter is kind of the same thing. So this is kind of like the normal size world. This is when you move, when you go to food shopping, you cycle to work, you are here. But now, how big is my nail? Well, I would say 1 millimeter. So 3 orders of magnitude is 1,000th, which is a 10 with 3 zeros. So if this is a -3, how big is an atom? Like, they invented this unit of measurement, which is the angstrom, which is exactly 10 at the -10 meters. Sorry, imperialists. Sorry, I don't know how much is it in. Probably you have an angstrom for foot and inches. But normal human beings use the angstrom, which is 10 at the -10 meters. So -10 by definition. And this is roughly, I think, the radius of an atom of hydrogen. I would say hydrogen. I don't know. Now, what is smaller than an atom? Like the nucleus is 10 to the -15, the electron 10 to the -18. So let's say electron 18. This is the smallest thing we can think if we didn't do advanced physics and quarks and muons and whatever. I'm pretty sure there was something smaller than that. But for the physics you studied before the university, I would say 10 to the -18 is about right, of the order of the smallest thing you can conceive. How big is the Eiffel Tower? 312 meters, so two zeros is of the orders of hundreds. How far is the moon? Now, you need to Google it. The moon is 300-ish thousand kilometers. So 300, 100 is 2, 1,000 is 3, so it's 5, but kilometer is not meter, so 2 meters is another 1,000, so it's another 3, so it's 8. So the moon is around 8 order of magnitudes of meters. So it's roughly 10 at the 8th. But you could argue, but this is 3,084,000. Should it be 8 or 9? I mean, it's 100,000 is 8 kilometer. 1 million kilometer is 9, because in meter is 1 billion, right? That, Riccardo, you convinced me. But when should I choose 8 or 9 since you want to drop the mantissa? That's an amazing question. When do you draw the line between 100,000? What is the point where 100,000 becomes a million? Since we all agree that 200 is very close to 100, right? So 100 is 100. 1,000 is 1,000. 200 is probably closer to 100. 900 is closer to 1,000. And I say yes. What is the point in the middle where I choose to go up or down? The dot 5 of the approximation of two integer numbers, if you know what I mean. Well, I'm pretty sure everybody of you thought 500, but I can tell you 500 is wrong. Riccardo says it's wrong. Let me refine. So the average between 100 and 1,000 is 550. I know it, it's 550, Riccardo, correct? Wrong again. Wrong again, wrong again. What is that number that is multiplicatively equidistant between 100 and 1,000, between 1 and 10? Well, what is the number that multiplied by itself gives 10 and divided by itself gives 1? Is the square root of 10, which is roughly 316. You didn't see it coming, huh? So 316 in log scale, that means if you look on the logarithmic scale, this is 2, this is 3, and this is exactly 2.5. So the square root of 10 is where you should draw the line if you are a bloody picky person like myself. Or if you understood the topic well enough, you could say, Riccardo, I don't care. 5, 6 is the same number. 2, 3 is the same number. There you go. If you're thinking that it doesn't really matter, you're really understanding the thing right. In orders of magnitude, we don't really care. But if you want to have like a mathematical approach to it, you could say up until 3,316. If you forget it, think it's very close to pi, 314, right? It's just a bit above pi. So from 100 to 316, it's 2. And from 316 to 1,000 is 3, and so on and so forth for all the numbers. I used the 100, 1,000. I should have used 1 to 10. On a 1 to 10 scale, 1, 2, 3 is 1, 4, 5, 6, 7, 8, 9 is 10. And I know, I can hear you screaming, Riccardo, that's not fair. 10 wins over 1. 10 has 4, 5, 6, 7, 8, and 9, and 1 has only 2 and 3. And I say, yes, but you live in a world of multiplication, not of addition. So multiply by 2 is the same fair game that dividing by 2. So 10 divided by 2, 5. So between 10 and 5, you have the same distance that you have between 1 and 2. You see, if I tell you that 2 and 5 are brothers, and you see that 5, 6, 7, 8, 9 are just blah, 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 because 5 is the brother of 2, then you see that the average is around 3. It's called geometric average instead of arithmetic average. It's the average of multiplication instead of addition. Instead of you doing 1 plus 10 divided 2, which is 5.5, you do 1 times 10 square root of 2, which is 3, 6, 3, 1, 6, whatever. Okay? The exact number doesn't really care. Now, back to us. So, if you want to say, coming back to the distance from the moon is 384. So, you know, instead of 8, we could take 9. But again, 8 and 9, no biggie. Okay, how distant is the sun? Well, everybody knows the sun is 150 million kilometers from us, right? So, how much is 150 kilometers? Million. So, 150 is 2. Million is 6. So, we're 8. And kilometers. So, we need to still add 3 to get to meters. So, it's 8, 11. 11 for the sun. Now, what is the second star after the sun? Well, the second star is Proxima Centauri, which is part of Alpha Centauri. Alpha Centauri is 4,300 light year. What is a light year? Light year is a measurement of time, right? No, it's a measurement of space, because the light is famous for going very, very fast. It has a fixed velocity. So how far does it get? Like, how far does my Ferrari get in a year? That's a measurement of space. Well, the light is even faster than a Ferrari by 6 orders of magnitude. We can calculate that. I don't know. So a year light is 300,000 kilometers. So it's 8 zeros times a day in seconds, which is 86,000, which is 5 zeros, times 365 days, which is 2.5 zeros, right? So in total, we have 16. We have 16 zeros. So that is the dimension of a year light. This is a completely, it's like, you know, like Italians use kilometers, the Brits and the Americans use the mile, and the astronomers use the light year. The problem is that in orders of magnitude, mile and kilometer are the same thing. Even inch and kilometer are only a few orders of magnitude away, but the light year, oh my goodness, this is 16 orders of magnitude away. So it's like 10 millions of billions away from the meter. So in these terms, Alpha Centauri is 4,000, so 3.5 order of magnitude, so let's say 19/20. The universe as we know it is actually 10 at the 10th light year, so we need to add 10 times 5, so maybe 11, 10/11 of this. So let's say 26/27. Okay, now we got to the end of it. The universe as you know it is long 27 zeros. So how big is the universe in meter? Is 1 followed by 3, 6, 9, 3, 6, 9, 3, 6, 9. So if you go a capo here, 1 billion of meters. So that means that if you put a person in one after the other, the human beings are 8 billion. You only consume the first 9 zero. you need 1 billion of planet Earth with similar population to fill up the universe. Okay, so the universe is like the cube of the order of magnitude of our population, right? There is one difference, but you know what I mean. So this is the universe. And what is the smallest thing? The electron. So how many electrons could fit in the universe? Remember, the universe the density of the universe is close to zero, so there is a lot of empty space. But let's say that tomorrow, with the bike pump that I have in my garage, I start pumping electrons all over the universe. And I have a couple of billions of years to do it. Well, how many electrons could fit hypothetically into the universe? Well, on a line, 18 in 26 stays 44 to 45 times. So monodimensionally, you would have 10 followed by 44 zeros of electron in a line which is as big as the universe. But the universe is tridimensional. So actually, and this is the beauty of orders of magnitude, the number of zero will be the cube of this. So the cube of this is 132/135. So can we say, if you say how many electrons would fit in the universe, the answer would be order of magnitude 130 something zeros. I'm actually approximating the number of zeros as big as this number is. This is completely mind-bogglingly big. Okay, so it's just to tell you, but this is interesting because that tells you also that the biggest and the smallest thing the smallest stays in the biggest, not more than 130 zeros from the other. Okay, a Google, Google, not the company, but the number, is 10 with 100 zeros. So this is like a Google and a half in log scale. Okay, stai zitto, non parlare di Google. Okay, so this is really interesting. Now, how many chess games can you play? Let's say that you play randomly because you're stupid, you just do checkmate. Okay, let's try another. Then the space of different chess game configuration has been estimated to be around 10 at the 110, 120, I think. So the order of magnitude of the chess games is very similar to the number of electrons in the universe, give and take, with tens of their magnitudes different. So it's incredibly complex. So it's quite surprising that computers can tackle this complexity. Okay. Now, I hope this was useful. So again, the beauty of orders of magnitude is you simplify the number and you just think about how many zeros are behind, and then you become increasingly fast to do multiplication, division. I remember once I had to calculate a transistor capacity, and it was something like the formula gave me like a pi multiply by 10 at the minus 15. It was pi femtofarad. Okay, the interesting thing is that femtofarad, which is minus 15, this was the important part, and pi, which is 3.14, this was not the important part, because then you would do a logarithm to calculate some other components, and what really matters is this number here. Okay, so what I'm telling you is that there is a universe in which the number of zeros of your number is the significant part. The part before, 2, 3, 4, 5, who cares? Now, let's get you past the test. Now, finally, how many tennis tables can you fit in this room? Let's get to the juicy exercise. This is the only use, this is the pragmatical use of this theory that will get you a job in a tech company, maybe, if you can digest what I just said. So, one thing that they can ask you when they try to hire you to see if you're able to manipulate the numbers fast and to get to the core of problems without getting lost in stupid details is how many tennis tables are there in this room. What I love about this question is that there is a lot of complexity and you can forget of that. And I think what you aim to do is you need to get the right order of magnitude in 20 seconds, 30 if you're slow. That's it, without using paper. That's what we need to do. And then you can refine and refine using paper and equations and what have you. So I think, how many tennis balls, the yellow one of Roger Federer, okay, tennis balls are in this room? So the first thing you tell me, oh, Riccardo, but I'm not into your room, I don't know. And that's the beauty of it, because when they ask you this thing without COVID, you would probably be in a room and you're like, but I don't know this room, I don't have a meter. Yeah, but you can roughly say, oh, I don't know, like this room, for example, is 2 meters times 3 times 4. It's really small, okay? Now, the beauty of this is that most room that you will deal with will be very similar order of magnitude, okay? Let's see it together. So, this is how big is the room, and how big is the ball. So let's say that the ball has a diameter of 8 centimeter. You could say 3 inches, okay? 8 centimeter diameter. The diameter of this is 8 centimeter. Now, what is the beauty of this? That the room is roughly in meter 24 square meters. And this, what is the volume of a ball? So I know that you say, oh, the volume of a sphere is 4 divided by 3 times pi times the cube of r. But actually, we could say the volume is 4, 3 pi, the half of this, which is 4 cubes. But actually, we could say, fuck it, I will just take the cube. What is the cube? 8 by 8 by 8, which is 512. Forget this, 512 cubic centimeters. Now, how many of this stay in this? Oh my God, we need to do a division. Now, a division of numbers is difficult, but a division of order of magnitude is easy peasy. You want to see that? Look at that. So, how many balls? So the answer, which is not 42, is 24 square meters divided by 512 cubic centimeters. Now the problem is that here we're not dividing meters with meters, but centimeters with meters. And you know that a centimeter, if you know Latin, centimeter is a cent of a meter. So this is a meter divided by 100 at the third. Remember that since it's a volume, a cent, so 100th of this, you need to multiply it by itself 3 times. So 100 by 100 by 100 makes a million. And this is the thing that most people tend to forget. So basically, a cubic meter has 1,000,000 cubic centimeter. If you want, a cubic centimeter of water is 1 gram, give and take, and a cubic meter of water is 1,000,000 gram, which is a ton. Think about that, 1,000,000 bloody grams. And in fact, you know, if this is 1 cubic centimeter, and you have 100 of this, and 100 of this, and 100 of this, it's clear that you have 1,000,000 of those little cubes in the big cube, right? So this is like 24 million divided by 500. Now, we could say this is 48 million divided, which is 48,000, right? We could say the order of magnitude is roughly 50K, okay? And this would be correct, right? Like we have roughly, let's see if the number 24 million, 48 milioni, yeah, 48,000. So the person who asks you this number doesn't want 48. They don't give a shit about 48. What they care is that it's something between 10K and 100K. Okay? Because maybe, I don't know, they want to know how much it's going to cost. And this means that, oh, let's say that they cost €1. To do this little experiment, you will spend between 10,000 euro and 100,000 euro, which is between $10,000 and $100,000, somewhere in between. And this is important. It's not going to be $1 million, but it's not even to be as cheap as $1,000. Okay? And if the ball is more expensive than $1, maybe, you know, the ratio changes. So this is what's really important. So order of magnitudes is when you want to be fast about multiplying or dividing things, and you don't want to bother with the actual little number there, which might change tomorrow. You know, you do capacity planning next year, this could be twice as that. Well, with order of magnitude, you stay on the same range. Maximum you add 1, and then you're fine for 3 years, 4 years. But if you want to get lost into this precise number, you know that the precision of that dies within the context of the exercise, and tomorrow this number is not usable anymore. But this, oh my goodness, how big is the universe? It won't change much. It will always be around this 45 in one dimension, or 120, 130 in the three dimensions. Okay, I hope that was useful. And by the way, the only people who use logarithms for living are actually musicians and sound engineers. If you think about it, the only measurement that is used logarithmically is the decibel. I think we would be in a much better place. Let me tell you a couple of things more. Like, let me tell you a couple of things more if you're interested. Number one, if I sing la, la, these three sounds, the first two were around, I don't know, 70 decibel, the last was around 20 dB. So it had an energy which was 100,000 times less than the other. Sound engineer found out that like people looking at sound are like, what the fuck? It takes me a lot of zeros to define like the energy in milliwatt of pressing a tab on my piano or an oboe or on a trombone is different. And they're different order of magnitude. So they decided to take the logarithm of this. So imagine if this, you could just, instead of using this number, you could use the green numbers. Well, those are called bell. And the decibel is just multiplied then by 10, because just human beings are so bad with commas that you need to multiply percentages by 100 and decibel by 10, so you get into human, right? So you could say, how big is Riccardo? Oh, Riccardo is 0 dB. And how big is the Eiffel Tower? Oh, is 20 dB. And how far is the moon? Oh, the moon is 90 dB. And how far is the sun? Or the sun is 110 dB. Okay, this is in terms of measurement. This could be the sound. That means that if I sing at 90 dB and you sing at 90 dB, what is the corresponding sound? This is a difficult thing. So how much is this plus this? If it was a normal measurement, it would be 180, but you know that two people talking at 90 dB, they won't have a sound of 90, but this is exactly 93 dB. Because, well, exactly, nearly exactly, because if this is 90 means that this is a 10 at the ninth something, and this is 10 at the 9 something. This is 2 times 10 at the 9, which in log scale becomes 90 plus the logarithm, 10 times the logarithm of 2. The log of 2 in base 10 is roughly 0.3, I think it's 0.299999. It's really, really close to this. And if you don't believe me, exponentiate 2 10 times, you get 1024. So 1024 is so close to 1000 that the log of 2 is so close to 0.3. Think about that. So that means that it's like 93.001 or 92.09999. Okay? And this is beautiful because, or what if 10 people sing at 90 dB? Well, 10 people is one order of magnitude more, so that would be 100. What about, so one person 90 dB, 2 people 93, 10 people 100, 100 people, well, this is 2 orders of magnitude, so 90 is 110. The only confusing part of the dB is that the person who invented it decided to multiply by 10. So that you need to think that you need to always remove, if you remove the 10, it makes a lot more sense. And let me put it in red. One person is 9, 2 is 9.3, 10 is 10, 100 is 11. So 10 people add 1, 100 people add 2, 1,000 people add 3. In decibel, you just add a 0 just because it's easy to pronounce and because 93 is easy to pronounce than 9.3. This is just the reason. It's pure aesthetic. The decibel is aesthetic. The bell is pure genius. Okay? So it would be nice to measure things like we do it all the time with meters and centimeters, but instead of using decibel for meters, we use meters and millimeters and kilometers. And when the kilometer becomes too small, we have a year light. But that's what we do. You know, we are just too lazy to use a decibel meter. We should use the decibel for meters. Then we could say, oh, how far is Alpha Centauri? Is 190 decibel. And how far is the sun? 160. And the moon? 90. And the tower, Eiffel Tower? 20. And Riccardo? 0. And my nails? minus 20 dB. As simple as that. Okay, so I hope I also explained a little bit about the decibel, which is cross-functional but maybe useful. Hope it was useful. Let me know what you think. Bye bye bye.